Hello everyone. So this video presents how to build a deep learning model by using transfer learning. So what do you mean by transfer learning? So transfer learning is a pre-trained model. In other terms, we can say it's a saved network, and the network has been trained on large data set. So basically, when you have large amount of data, like whenever you are working with images, videos, or some high complex data, so we do not have much capacity to process that thousands of images or thousands of videos. So what I'm trying to say is, whenever you have a large data set, so we do not have the capacity to process or to build a deep learning model on such kind of data. So in that case, better to use a pre-trained model. So pre-trained models are the already built models, and these models are built on some millions of images. So they already know how to uh, solve a problem or how to process the images, right? So that's why, so there are pre-trained models. We can use those pre-trained models on our test data or on our new data set, so that you can develop an efficient model. So then next the question is, how do you do this? So there are two approaches to implement this transfer learning on our custom data sets. The first approach is feature extraction. It means you can use the representations learned by previous network to extract meaningful features on the new data set. So from the existing model, we just use the features, and on top of that we add a new classification layer. And point to be noted is, here no need to train a network from scratch. Understand? So no need to train a network from scratch. So we just use the features of the existing model. On top of that, we add a classification layer which can do the classification, and this doesn't require no training a model from scratch. So that is the point to be noted. Then the second approach is fine tuning. Here you can unfreeze few top layers of the existing model. On top of that, you add a classification layer and then do the classification. So I'll be explaining these two methods in this video. So you'll be learning how to use the first method and how to use the second method to build a deep learning model. And the data set that we are going to take is cats and dog classifications, cats and dogs image classification layer, classification data set. So basically these are the sequence of steps involved. First we need to understand the data set, right? So once you understand the data, we'll define a pipeline. So that pipeline specifies how the classification is built, how classification is done. So at first, as usually, we import the libraries. Like here I'm importing OS. OS stands for operating system, and we import NumPy. Why do we import OS? Because to work with the file system, you need to use OS. And then NumPy, use for creating array, and then matplotlib for data visualization, and you are also importing TensorFlow here to build a deep learning model. So once these libraries are compiled, and we have the data set, right? So TensorFlow provides you TensorFlow data sets. You can also see what are those TensorFlow data sets provided by the system. So here you can just click on this http://tensorflow datasets. So that provides you the list TensorFlow data source. So it's a collection of ready to use datasets. You can use these datasets for practice. So here you can see the examples also, like the explore dataset with know your data, introducing TensorFlow dataset. So there are, you just browse this URL. Understand? You just browse this URL, so you can see what are the predefined datasets. Right? You can see what are the predefined dataset and how to load them. So this, so we need to install this library pip install TensorFlow datasets. So from this library we'll be getting the cats and dogs datasets. Next, importing TensorFlow datasets as TFDF. TFDF is the alias short name, and we want to disable the progress bar. So TFDS dot disable progress bar. So once the library is imported, so directly we can call this function TFDF dot load, and the folder is cats versus dogs, and we are splitting this data set after loading into uh, three parts: raw train, raw validation, and raw test. And you can see the dimensions of these three data sets. So 0 to 80%, which is train, 80 to 90%, so totally 10%. So that is a validation data, and 90 to 100 is a test data set. So this data set is no, loaded and split it into three parts, and as supervised true means we can use this data set for binary classification, because there are two classes, cats or dog. So when you do this for the first time, the data set is downloaded. You can see downloading and preparing data set. The size is 786.67 megabytes, and it also shows the path where it is going to download. So this will take couple of no minutes, so let's wait. So the data set is downloaded now. So after that, so we can display the sample image. So getting the label, so get label name is equals to we have the metadata set downloaded here with info equals to true, means we are getting the metadata set, and then label and converting that integer to string, so this gives the label name, and writing a loop here for image comma label in raw train dot take of 2, means we are getting two images here, and plt dot figure, so creating object to the figure and then showing the image and also showing the label as a title. So when you run this, you can randomly get two images here. So this is the first image, take of 2, so this gives the two images. So this is the first image and the label is dog, and this is the another image, the label is dog. Then we need to format the data. So TensorFlow uses the format, right? So we want to resize the images to the fixed input size, and the data is scaled in the range of no, -1 to 1, and the dimension of the image size is 160, means 160 by 160, width and height. And we are defining a function format example, in which we are converting the data type of the pixel values to float 32-bit, and then dividing the pixel values by 127.5, subtracting -1. So it means the data is scaled in the range of -1 to 1, and resizing the image based on the this one. So it's the image is scale no, resized to 160 by 160, and then we are calling the above function. We are calling this function on three data sets: train, so raw train dot mapping with the function, then raw validation dot map, then raw test dot map. So the function is applied on three data sets. Then setting the batch size to 32 and the buffer size to 1000, and we are also suffering the images train dot shuffle, shuffle buffer size which we have mentioned 1000 dot batch size of 32. So the data is shuffled, so three data sets are shuffled. And after that, so we are just inspecting the batch of the image. What is the batch of the image? So when you run this, the batch size is 32 and the shape is 160 by 160, and this is the depth of the image means the number of channels used to represent the image. So if it's a colored, then the number of channels are 3. If it is a black and white, then it's 1. So once we have formatted the data, the next step is creating a model. So to create a model, we can use pre-trained network. So MobileNet V2 is one of the pre-trained network which was developed by Google. Understand, which was developed by Google, and this data set has totally 1.4 million images. 1.4 million images and 1000 classes are there. So in those 1000 classes, the cats and dogs is already there. So that means the pre-trained network knows how to identify or no recognize cat or dog. So we'll use we need to download this model. So specifying the shape here, and then this one tf.keras.application.mobilenet v2, specifying the shape, then include top equals to false. So we don't want to include the top layers on top of the existing. We want to add a classification layer which does the classification. So weights are used by weights is equals to ImageNet. So ImageNet is the data set. So the weights of the ImageNet data sets are used. Then the pre-trained model is downloaded. When you run this cell, you can see the model is downloaded, and we want to display the size of this pre-trained model feature batch. So feature batch equals to the base model. So we have given the name as base model, and then image path. So this is the feature batch. 32 is the batch size, and totally now 1280 pixels are used to represent the feature black. So first we are using the first approach, that is feature extraction. It means, I can say it again, feature extraction means use the features of the existing model and then add a classification layer which does the classification. So base model dot trainable is equals to false. As I mentioned before, we don't want to train the base model, so which is false, and we are just displaying the base model dot summary. So the summary gives what are the layers in the pre-trained model. So here you have a big list. And it displays all the layers in the existing model, right? And then it shows the number of parameters used in the existing model. So these many parameters are there. So on top of these layers, we want to add a classification layer. So before that, we also use global average pooling, so which will perform the average over all the spatial locations which are 5 by 5. So tf.keras.layers equals to creating object to the global average pooling layer, and then passing the parameters feature batch to this global average pooling, and then printing the shape of this. The shape of this is 32 is the batch size, and the images pixels are 1280. 1280 is the number of pixel values, is vector size, we can say. And on top of the existing, we are just adding a classification layer. This is the dense of 1, so single classification, whether it's a cat or dog. So adding a dense layer which will make the prediction, and then checking the shape of this. So the shape is 32 and 1, batch size is 32, single outcome. Now we are defining a model. So model equals to tf.keras.sequential, and this is your pre-trained model. Next we are applying the global average pooling. Next the prediction layer. Prediction layer means the last layer, which is classification layer. So this is the actual definition of the model. So as you know, once the model is defined, the immediate step is compiling the model. So while compiling the model, you need to specify the important things like what is the optimizer and what is the last function, and then how do you evaluate your model. So optimizer is this RM's prop. Learning rate, we are specifying it as 0.001, and this is customized value. so you can change it. And it's a binary classification problem, so the last function is binary crash entropy, and the metric of evaluation is accuracy. So the model is compiled. After that, we are checking the summary. So in the summary, on top of the base layer, so this is mobile net. On top of that, adding the global average pooling layer, and then adding a dense layer. So this is the final model. And then total of layers trained variables, so only two: global average pooling and the dense layer. So the length is 2. So we don't want to train the model from the scratch. So on the top of the existing one, we have added 2 layers which are to be trained. Now we are doing the training. So initial epochs we are mentioning 10 only. So this is also not fixed. You can increase or decrease this number. And validation steps we are mentioning it as 20. Then we'll see the performance of this model. So initial performance, you see the loss is 0.71 and the accuracy is 54%. So we can print this. So 71% is the loss, and 0.71 is the loss, and 55% is the initial accuracy. Next, we are fitting data to the model. So while fitting data means model learn from the training data. So fit of train batches, epochs we mentioned 10, and validation batch we all mentioned. So you can see the compilation has been started. In epoch 1 of 10, there is the initial loss and accuracy, and as you know, loss is decreased and accuracy is always increases. So you can make a notice of this. So this will take time, understand, this will take time, so have a patience, and let's wait for the complete epoch execution. So after completing epoch 1, the training loss is 0.2 and validation loss is 0.08, and the validation accuracy 97% and training accuracy is 93%. So there is a difference between the training accuracy and validation accuracy. So let us complete these 10 epochs. So after completing 10 epochs, you can see the loss is reduced, the training loss is reduced to 0.04, and the training accuracy is 98.51, validation loss is 0.0479, and the validation accuracy is 0.98. So it's a pretty good model, and the same thing we can show by using a matplotlib. So getting the training accuracy, which is equals to history of accuracy. So we have saved the results into the history, right? So from history we are getting the accuracy, training accuracy, and validation accuracy can be retrieved by using val underscore accuracy, and this loss, training loss, and validation loss. So we are plotting a subplot of 2 1 means 2 rows 1 column. In the first graph we are showing the accuracy, and in the second graph we are showing the loss function. So I hope you have the fundamentals of matplotlib, how to do the data visualization. So in the first graph, so training accuracy is increased and validation accuracy also increased, and in case of the second graph, the loss always decreased. So this is a pretty good model. So the accuracy we got is around 98%. So this is using the first model, first method, that is feature extraction. Next is fine tuning. So here you can unfreeze few layers of the existing model. In the first method we just use the existing layers, on top of that we'll add a classification layer, whereas in the second method we can use the few layers of the existing model, and on top of that we'll add classification layer. So also in the first method we set a base model dot trainable is equals to false, means we don't want to train, but in the second approach we train, so trainable is true, and then showing the number of layers. So number of layers, and fine-tuning starts from the layer number 100. So totally we have 154 layers in the pre-trained model, and we want to fine-tune from 100. So then compiling the model here, so specifying the learning rate, and then these things are all same. The last function is binary crash entropy, optimizer is no RM sprap, and then metric is accuracy. So the model is compiled here before that only, and then taking the summary base model dot summary. So on top of this, on top of the base model, we are adding the global pooling layer and dense layer, then checking the length. So length of this is 56. Understand? So we have how many layers from that pre-trained model? Starting from 100, so 54 plus we are adding the global average pooling and dense, so totally 54 plus 2, which is 56. So the total layers trained are 56 now. The process is same, so right, so we fine tuning start from the epoch 2, then initial total epochs is equals to initial epochs plus fine tuning epoch, that means 10 plus 2, which is 12. Then fitting the data to the model, so this will also takes a couple of minutes, so we should wait. You can see it's almost finished. So the accuracy training is 0.98% and validation accuracy is also 0.98. So fractional difference is there. So this is also a pretty good model. So once the model is built, we are getting the accuracies and losses, and then having a plot. So you can see how the loss is decreased, and the vertical line shows the fine tuning. So we have started fine tuning, then the loss is decreased and then increase like that. So training accuracy decrease and increase, but finally the accuracy is around 98%. Similarly, loss also increased and decreased. So this is also the good approach. So what is the benefit of transfer learning is, as we do not have the processing power and storage capacity to store some millions of images and processing them. So in that case, the better option is you can use pre-trained models, and these pre-trained models are already saved networks, so they have been learned how to recognize any kind of images. As I said, the MobileNet V2 model has been trained with 1.4 million images, and it knows how to classify 1,000 classes. There are 1,000 classes of images trained by the model. So on the large data sets, so we always go for applying transfer learning instead of building a model from scratch. So that's it from this video. So I hope you got you found some benefit from this lecture, and I hope it also helps you when you have a large data set. Better go with no pre-trained models. So that's it from this. So do subscribe and do comment and do like our videos.